The colours that we see are incredible. Some are vibrant, some are dull, and sometimes our brains just make them up. Take a look at this flag. Keep your eyes focused on that white dot in the centre and don't look away. You may want to pause the video for 10 to 15 seconds to really let your eyes adjust, because now you're looking at a white screen, but chances are that at least briefly, you saw red and blue shapes where there weren't any. Your eyes just lied to you. What other colours could your brain be lying to you about? Let's take a look at how we look.
Visible light is broken up into colour by its wavelength, with red having the longest and blue through violet having the shortest. However, our eyes don't actually measure the wavelength of light. Instead, we rely on millions of light-sensitive cells in the back of our eye, called cones. Humans typically have 3 types of cones, red, green and blue, that are each sensitive to different, but overlapping, wavelengths of light. To see colour, our brains measure and compare the amounts of red, green and blue that our eyes receive. Let's look at yellow. When yellow light enters our eyes, our red and green cones are stimulated. It's this mixture of red, green and hardly any blue that to our brains is yellow. But because of this, if you stimulate your red cones with red light and green cones with green light at the same time, no yellow light at all, your brain will still think it's yellow. Take a look at this yellow LED. When I get right up close to it, we can see that it's actually just a red and a green LED right next to each other. We've been tricked.
It's this colour mixing trick that allows digital screens to simulate almost any colour we need just using red, green and blue light at different brightnesses, or more familiarly, RGB. And it's what allows you to see magenta, a colour that doesn't exist on the visible spectrum that your brain just makes up. There is no wavelength of magenta light, or pink light for that matter. It's what happens when your brain fills in the gaps when it receives red and blue light without any of the green in the middle. That's cool, but we see pink and magenta things on a daily basis. Colour is much weirder than that. We can exploit after images to glimpse into colours you can't find in any real object. Impossible colours. When we looked at the American flag earlier, we saw green turn to red and yellow turn to blue. These pairings can be explained by the opponent process in our eyes. Post-processing on the red, green, blue inputs from our cones.
Behind the cones in your eyes, pairs of opponent cells add and subtract the signals from your cones to give 2 new outputs, red versus green and yellow versus blue, remembering that yellow is a combination of red and green. In each pair, the opponent cells compete. Either one is stronger than the other, or they cancel each other out. Your brain combines the red-green and the blue-yellow result to get colour.
This opponency explains the after images we saw of the strong colours in the flag. Let's look at green and red as an example.
Your eyes naturally move around rapidly, so the cones in one spot usually receive a constantly changing signal. But if you keep your eyes still, say by staring at a green circle, eventually your green opponent cells will get tired and fatigued and send less and less signal. Suddenly, if you switch to a white screen, whereas normally the red and green should react equally and cancel each other out, the tired green cells can't match the fresh signal of the red cells right away. Thus you see red, at least until green gets themselves sorted out again.
We can exploit the fatigue of our opponent cells by staring at a strong colour, then glancing at another, and in doing so glimpse unreal combinations of colours. These are called chimerical colours. How about a green the greenest green your screen will deem to show? We can do that.
Like the flag before, stare at the cross in the centre of the red circle until the edges start to blur. Then, quickly cast your glance over to the green square. You should briefly see an even greener circle inside the square. This is a hyperbolic colour, pushing saturation beyond the limits of the spectrum. Consider how even a pure green wavelength still stimulates the red cone a little bit. This hyperbolic green swings even further green. What about a bright orange that's simultaneously lighter than white? We can glimpse this self-luminous orange by looking at its opposite, cyan, before switching to white. Colours like this appear to glow even when printed on paper. This last example works best in a dark room. If you stare and fatigue your yellow opponent cells, then glance at black, you can see Stygian blue, a subtle colour that's like black but saturated blue. I've included some links below to more chimerical colour templates you can find online.
After images and impossible colours may sound strange, but really they're just consequences of the strange ways that we make sense of the world around us. It's all just a trick of the eye. Are any colours real?